Good afternoon, good morning, good evening, wherever you are joining us from. We are welcome to the series 2 of our machine learning with our facilitators are here and stand by for us. And I want to assure us today, it's not going to be as usual. We are moving ahead and ahead and ahead. And I want to encourage every one of us, please let's try and do it on our own too. Ask questions, make comments on your code. Thank you. So join me as I welcome Dr. Olumide Adesina.
Yeah. Thank you. Yeah, thank you, Dr. Okay. Well, we are going to share the slide. Well, I want to welcome everyone. We started this series last week, though the concluding part of that was done earlier, the machine learning aspect was treated. We started with linear model, and last week we picked it up from a classification, talking about logistic regression, discriminant analysis. That was what we did last week. And we were able to conduct some analysis based on the theoretical aspect that was discussed. Now, we started with binary logistic regression. Meanwhile, before we launch into logistic regression per se, the procedure for conducting machine learning exercise was also explained, talking about different types of classification and the rest of them. So I want to ask those of us that were around last week to maybe one or two to help us to have a kind of recap of what we learned last week, so that I can be sure that we're actually following. So I'll be calling Odebode Sunday in 5 minutes or less. Give us what you learned last week, so that I can be sure, or we can be sure that you are following. I know you were around last Sunday, or last Sunday actually. So over to you, Odebode Sunday. You can unmute your mic. Unmute yourself.
Hello, please. Can you hear me, sir?
Yes.
Can everyone hear me?
Yes.
All right.
Yes.
Okay. Thank you, sir. Actually, last week I wasn't with my system was down too, so I was only following with my phone, but I was able to learn some things, especially the introduction to machine learning, and sorry, I'm trying to open my system now.
Okay. Any other person that was around last Sunday? Ajayi Yetunde, let's hear you. Let's hear from you. Unmute your mic and speak to us.
Good evening, sir.
Yeah, good evening.
Yes, sir. I joined the meeting late, so.
Okay, even as you joined late, what did you learn last week? What can you tell us about last week? And did you have the video actually?
Flashback.
You have the video.
I'm trying to flash because
What?
I'm trying to open my notes. I will get back to you, sir, in a short while.
Okay, so we are, anyway, without wasting time, we're still going to have this from you, but without wasting much time, we are going to be, we are going to what we have for today, which happened to be the continuation of last week. Doctor, can you kindly move the slide to page 1? The slide, please.
Can you see it?
Yes, I can see it. Now, last week I talked about multi-class case. In the case where we have more than 2 classes. So, and like I mentioned earlier, last week, logistic regression has some limitations in fitting data response variable that in case of multi-class that have more than 2 classifications. Now, in this case, we are considering a data set built into R called iris. Iris, I think in biology, you did, about when you talk about flower, we have iris and different part of it. Now, and the data set is contain the measurement of 4 different attributes: the sepal length, the width, sepal width, sepal length, and the species. The species happen to be the dependent variable. So, and this is what we want to fit it and be able to predict based on the available data. And to do that, I already told you to install some packages that will enable us to conduct this session. So now let's proceed. Next slide, please. Doctor, okay, next slide. Okay, all right, then, and to do that, the first thing we are going to do basically is to conduct the descriptive analysis, the explorative data analysis, which has been, that portion has already been, it was on the previous slide. Then we also have to conduct the what was it called, the plots, which is the bar charts, the what was it called now, the scatter plot and the box plot. And you can see the code associated with that on this particular page. Okay, now please, let's go to the next slide. The next page. Okay. Now, that's the previous slide we're talking about is just the descriptive part. Now, this particular one, this particular slide is just telling us how we are supposed to partition our data into training and testing sets. And when you look at the code, you look at this particular one is partition, create data partition is a function that we are going to use. You know, like, you know that there are different ways of separating data. This is one of them. You can either use sample, you can even use data directly, but in this case, in this particular case, we're able to determine the percentage of data we want to partition for training sets. Okay, then the next thing there is to fit the model with LDA function. You can see the next line that follows, fit underscore LDA. When we do that, it's going to give us the required outputs. Okay. Now we go to the next slide. Now, when we do all this, we are going to obtain the the output, and which we are going to discuss. And after that, during the class, you are going to do your own, which is what I did is linear discriminant analysis. But here you are going to conduct quadratic discriminant analysis. Now, the difference between quadratic and linear, you have to fit it, is just change LDA to QDA, and you are going to use the same data set. Now, when you are done, where to submit the results is already provided. So, in other words, some people already, they actually clamoring for certificates, which after every school you should be given, but we need to be sure that the people in our school they are actually following, so that we're able to identify who to give the certificate to. And that is why we have decided to include exercise and practical sessions so that you can follow adequately. Now, after the exercise, that is the end of the classification part. Now, the next thing is to discuss the penalized regression. Penalized regression. Now, if you follow from last week, those of you that asked for what we did last week, one of the things we did last week is how to reduce variance. And to reduce variance, we introduce bias. And one of the ways to introduce bias is to penalize. And we are going to be talking about the process involved in penalized regression, or we can even say regularized. Now, we are talking about, there are three basic methods, or let me say two basic methods, after which you have elastic nets and some other methods that have been introduced. Research is continuous. Statistician keeps coming up with models in this regard. So, but the first of that kind is the ridge regression. The ridge regression. Then we also have the lasso. The lasso, which means least absolute shrinkage and selection operator. Then the elastic net is a hybrid. Hybrid, bringing the two together. And usually the objective of hybriding two data or more is to improve the model and make them better fit. So that is why we came about the elastic nets. All these methods have their strengths and weaknesses against each other. So by the time we dig deeper, you'll be able to know all this. Okay. Now, next slide, please. Okay, next slide. We have the model here. You can see the model. We can see the model.
Yes.
The model for ridge regression is as given in equation, that equation. We can see the lambda there. Lambda there is a tuning parameter. Summation j equals to 1 to p. B squared subscript j is actually the penalty part. We can see, okay, now we can now see this residual sum of square. By the time you add everything up, that gives you your ridge regression. Okay. Now, next slide, please. Okay. All right. So we can see the shrinkage penalty. Then the lasso, the difference between lasso and ridge is that is the absolute value of beta subscript j was added, while the other one, it's just b squared subscript j. Okay. And I think this has been explained earlier. You can see the ridge, penalty for ridge is that, and that of lasso is the absolute value. Let's proceed. Okay. Now, to do that, we rely on simulated data initially. We are using a simulated data set, and we are considering count data. You know that count data is discrete. So now, in this particular simulation,
Dr. Olumide.
internet is a network. I'm back.
Okay.
Okay, I'm back now. Yeah, so discrete variable distribution. Now we are considering, when you're able to if you want to simulate count response from discrete variable, there's condition attached. The condition is that your beta must be greater or equal to, greater than 2, actually, greater than 2. That is for under dispersed. Now, there's a difference between under dispersed count data and over dispersed. Under dispersed is the case where your variance is less than the mean, while over dispersed is a case where the variance is more than the mean. Equidispersed is when both are equal. And that is why Poisson distribution is not actually, Poisson regression is not actually suitable in most cases, because I can only find data that have equal mean and variance. So that is why we are looking at simulating from discrete variable. Okay. Now, we also try to simulate our different value of theta naught. You can see theta naught we say is 0.35, theta 1 0.25, and theta 2 like up to get to theta 5. Those are the parameters that will contain in that particular model. Now, next slide, please. And you can see the log link. You can see that it has a log link, and you can see the specification. Okay. Now, let me quickly discuss this before we go to the main house studio. Now, the idea behind this, I'm trying to see. Okay. Now, when you want to simulate, before that, over the week, I asked you to install these packages so that you'll be able to call any function that is required here. Now, all these packages will help you to do certain things. Now, I talk about DReg. With DReg, you'll be able to get a simulation from discrete variable. And even for simulation purpose, you can use Reg, W-R-E-R-E-G. Then GLMNet talks about the function that you use to obtain your penalized regression is available there. Theta-vars, the correct, and LM-ridge. With LM-ridge, you'll be able to conduct ridge regression without having to do a lot of programming because the function is already there anyway. Now, looking at the specification now. For you to conduct this, you have to specify your theta naught to be 0.35, like I described earlier. Then looking at the beta, look at beta. Beta is already specified to be 2.8. Now look at the code that follows. You look at it very well. With this function, you'll be able to get the response variable that is required. You'll be able to get the response variable that is required. Okay. Now, let's go to the next slide. Please. The next slide. Now, for the next slide, we are talking about splitting our data sets into training and testing. Splitting into training and testing. To do that, we have train, sample. You know, don't forget that our knob is 1,000, Abi. Here, our knob is 1,000, already defined the number. That set.seed. When we use set.seed, we are creating initial value, such that if you go again to do the simulation, you will get the same result. That is why when you see set.seed, actually helping you to manage your simulation. Okay, now we can now see the code that follows. Okay, sample 1 to n row, number of row, which is 1,000, comma, that is the sample, then size, n row, x over 2, meaning that size of 500, because already taken from 1 to n to number of row, then comma 500. So talking about 500 samples. Then we go to our tests. You just negate the number from the training set. Then we get our set test. Now the reach. Now we want to conduct reach. Okay, reach mode. That is reach model. Then we talk about GLM net. Like I said earlier, if you don't call GLM net, you may not be able to do this. So we have our GLM net, then X train, that is, then we have Y train, alpha is equal to 0. Why is alpha equal to 0? When you say alpha equal to 0, you are saying you are conducting ridge regression. But when you specify that alpha equals to 1, you are conducting lasso. So now the next function now says coefficient. Now it prints out the result for you. Now the next the right hand side now want to conduct 10-fold cross validation, because the default there is what is 10-fold, and that is why this function, when anything you do here, it will give you your what cross validation as expected. Then we now say, okay, best lamb. Best lamb simply means, here we specify that our lambda, we want to obtain the best lambda now. So we now say cross validation is already out. That $sign lambda dot mean, that is minimum, the lambda that will give you the minimum cross validation. That is what we are interested in. Are you getting me? So don't forget that last week we talked about cross validation, and we talked about leave out 1 and the ridge and the k-fold. Here we are using k-fold cross validation. Now you can now see that with the best lamb, we'll be able to get our ridge, we're able to get our the value expected. Now look at this. Now say SSC, sum of square error. Now just write the code mean ridge dot pred minus the way it is done, the predicted value minus the actual the y squared will give you SSC. Then the next line gives you the expected what's it called, the output based on alpha equal to 0, because we're talking about ridge regression. Then the following line also is actually talking about the cross-validation based on the model, based on the cross-validation that we have obtained before. Then we have optimal lambda value, which actually minimizes. I'm trying to access the Zoom now. Okay. Anyway, let's go to the next slide. Shortly, we'll be entering the Zoom, the practical session. The next slide. Okay, want to find the coefficient of the best model. Then what do? We also follow that procedure. Okay, we obtain a coefficient. We obtain the coefficient, and as expected. Now, what happened in the case of ridge regression? Ridge regression shrinks coefficient close to 0. It will shrink the coefficient close to 0. That's why it is called shrinkage method. But in the case of Lasso would automatically remove any variable that is not useful. And Lasso does variable selection. It does variable selection. And let me also mention that when your lambda is equal to 0, automatically that takes you back to what? To ordinary least square. It takes you back to ordinary least square method. Okay. So now let's proceed. Okay, now we can see, let me go to the right hand side now. The right hand side, look at the formula for obtaining sum of square error, sum of square total, mean, MSC, and all that. Then R square. You know the formula that you are used to in your regression analysis. Okay. Now, with this, if you use a package called LM-Ridge, it will give you all this without having to do the coding by yourself. Okay. All right. Now let's go to the next slide, please. Okay. Now that's what I said. I said LM-Ridge, using the LM-Ridge package. After we have installed the package, then after we have installed the package, we go ahead and follow this line, use this line, we call it require LM-Ridge, then the mode, Y regression X, data, we have our data frame, then we have our scale, K is equal to what? Best lamb. K is equal to what? Best lamb. So with this, then we now do various plots. We do various plots. Okay. Okay, may I say that Doctor, okay?
I tried to mute one of your speaker. Are you there now? Hello, sir.
I'm here.
Okay. I tried to help you mute one of them so that you can connect.
Okay.
Which one you want to use so that we can leave one?
Okay, let me use my device, my phone.
Okay. Okay.
Yes.
Connect the two, just mute one. Exactly. Should I stop sharing?
Yes, let me mute one. No, don't stop sharing. You know the reason? The R Studio has not still come up.
Oh, okay. Let's continue.
But if I can use, I mean, if that be used, I may use R then. Because
no,
I
let's
don't know.
continue with this because
Okay.
using R to teach R Studio, people at times mixed it.
Okay.
That was what happened the first day.
Okay. So let's proceed then. Okay. All right. Now with these plots, we can see various plots that can be conducted using the package. Next slide, please. Now, Lasso, we can see, I may not need to go through the Lasso. It's just a replica of that Ridge, but the difference is when you are conducting Lasso, you just put 1 instead of 0. 0 is for Ridge, while R5 plus 1 is for Lasso. Next slide, please. Okay. Next slide, please. Next slide. Next slide. Next slide. Okay. Now, after we are done with all this, we are going to download these particular data sets. This happened to be exercise 3 because there are 3 exercises in this particular lecture, which you are going to submit to Data Analytics, and you copy the other email address provided. Okay, so we can now go to the R Studio. I'm not able to share, and it appears unpleasant, but we can do with what we
Can you see
have.
it?
Yes, I can see it. I can see it. The mic is running up and down. I can see it. Okay. Sure. According to the slide, can everyone see the R Studio? Can we all see it? Can we see the screen?
I think so. Let's just continue.
Okay. Now, the first thing there is to conduct the linear discriminant analysis. Okay. Now, to do that, we are going to call the library caret. Then the data we need here is what? Is iris. Then we conduct, kindly help us run line 4 to line 7, or even up to, well, yes, to line 7. In fact, the install is not necessary because for me, it's already installed here. So, yeah. Okay. So, yes, that's what he's saying. Okay. Now, we can see the dimension. Dimension is 150 by 5. Okay. So we can see the output.
Are you also sharing your screen?
I'm not sharing.
Okay, you are just doing it on your own side.
As a matter of fact, the Zoom on the system went off, trying to come back. Okay, I'm trying to join again. I'm trying to join so that I can see it clearly from the system. Okay. Okay, yeah, I can see. Okay, the thing is blurry somehow. It's not so sharp. It's not so sharp.
So you can see the iris now. Just look at the one I share.
I'm looking at it, but the screen appear blurry, some whitish. Is it how others are seeing the screen? Hello?
Yes.
Is it only me?
Can you see it now?
Okay. Just coming up. Okay, I think it's sharp now. Yes,
Oh,
it's
okay.
better. Oh, that's gone blurred again.
It's your network. Probably you off your videos.
Okay, I should off my videos. Okay.
Yeah, just off your videos and
Okay, okay. All right. Off now. Oh, it's better now. Okay. So we have the summary. Look at the histogram. If you do line 12 to 16, it will produce the histogram. Kindly help us with the histogram. You see color still blue.
yeah.
Okay. Okay, the screen is sharp now. Yes, we can see the histogram. So this is the command. Now, like you know, if you have this script already and you need to produce histogram elsewhere, you can adapt this to fit your data that you have. Then let's go to the scatter plots. Scatter plots. Okay, you can see the scatter plot, the stepper length, but the scatter plot is basically for stepper width and length. Is two-dimensional. Let's do the box plot, please, before we proceed. These are the explorative analysis we do. I think we did this lecture 2 of R earlier, but this just anytime you have any data set, it's expected that you conduct explorative analysis. Okay, you can see the box plots. You can say that I think setosi appears to be symmetric, while versicolor and virginical are kind of skewed. So now let's now go to the next, the basic thing, the major thing, the major analysis. Okay, now we want to now create train testing data. I want to partition. Okay, now If we do line 36 to 38, that gives us our training and testing set. Okay. Now, if you don't want to use partitioning procedure, and you just want to take 1 to 100, okay, or maybe just determine the number of out of 150, okay, let me take 100. So you can also follow this without having to use create data partition function. If you have a predetermined number that you want to partition, you can just use this, the line in 40, on the line 40, the script in line 40 to do that. Now, let's conduct our linear analysis. To do that, we need library mass. Now, we call in our library. Then the next thing we do, just follow this, the line of line 44. The LDA function tells you that you want to conduct linear analysis. Your dependent variable, which is categorical, is species. Then your data. You know, when you do this, it's showing that, okay, subjects other variables as independent variable. So we do that. Then we run line 46, gives us the coefficient. Okay. So that's the coefficient. So we have our linear LD1 and LD2. Now, this is just, you know, the normal coefficient that you have when you are doing linear regression. Okay, we say, okay, beta naught plus beta 1 x1 plus beta 2 x2, beta 3 x3. So that is what this LD1 is saying, linear 1 and 2. So that will be used for prediction purpose. Okay, so let's go to the next line. Okay. Let's predict now 48, 49 and 40 and 50.
I've done that.
Now we can see our prediction given what we obtain when we use the tests, when we use the training data. And that's what we have. And it's saying remove, we can see that tests, comma -5, meaning the 5th variable. So we can see what the prediction is like. So by implication, what we did, we used 80% of the data set for training and testing for what? And that's what we also use for prediction. You can see that we have 30 predicted values. You can see original and predicted. You can see. Now, how we want to test how efficient the model is. So the next line, which is 52, we want to check how accurate the model is. We now run line 52. We can now see if you run that, they are the same. For each class, you also obtain the same prediction.
Sorry, you break, Dr. Adesina.
Yes, please.
So where we are now is from run line 52, because we cannot hear what you are saying. Okay, line 52.
Okay. Can you hear me now?
Yeah, go ahead.
Okay. Now let me scroll it up a bit, please. This no, the script, the result. Okay. Now you can see the original data predicted. Let's now scroll down towards the end gradually. You will see that the predicted and the original, they are the same in each case, Tabi. Is there anyone that is different? I don't think so.
They are the same.
So they are the same. If the initial one I did, the one on the, what's it called? On the slide, I used 0.95. I've changed it to, in that, when you run that way, to give it just 5 predictions, because so that you will see it, just very small predictions. But here we have to run through 30 and see. So this accuracy measure is just telling us that what? It is 96.7% accurate. So, and okay. Now let's go up, please. There's a line that there's something that we need to do. Okay.
Exercise 1.
44, that line 44.
Okay.
Just copy it and paste it. Just copy it and paste and run. No, just the left-hand side. Left-hand side. Left-hand side of line 44. No, left-hand side. Just left-hand side. Okay. Yeah. So let's run that one. Okay. You can see a more comprehensive output here. Now, what is when it says prior probabilities of groups? You can see that, like I said earlier, I said 30% of, no, I think there are 150 data points. Each of them are 50, 50, 50. So we can see that this particular probability shows that there are only 33.3% of each classification of each class. Okay, look at the group means. You can see for sepal length, sepal width, and the rest of them. You see their group means there. Then the coefficient, I think this was obtained earlier. You can see the coefficient there. Okay, scroll down, please. On the results. Okay.
Yeah.
So, yes, that's the last, Abi.
Yes.
Okay, there's a pen here blocking my own. So we can see the proportion of trace. Okay. So it shows that LD1 mostly describe the relationship or account for more of the predictions relative to LD2. Okay, now exercise 1. On the line 54, it says conduct quadratic distributional analysis and obtain results. So you are going to replicate this same thing, but what you're going to do differently is, instead of using LDA function, you are going to use QDA function. And don't forget, from last week, we're able to identify that QDA, you can see, is more accurate than LDA. So should you have data set that you want to analyze, you could do a comparative analysis, because I can say, okay, so author said this. My result is a confirmation or it deviates from what the person said. So with that, you have come up with something, is a result. So, and that is just that. So I'm expecting this, I can say we are expecting it because it's going to our email address, and be able to ascertain who and who is following us and is worthy of being certified. So we are going to conduct this, produce your scripts as you have been doing. Don't forget in lecture 1, if you don't have it, ask for it. You are told how to save your scripts. Save your scripts, new scripts, save it somewhere. Then also your results. They want to see your results and to identify and to ascertain that you're actually following us. So let's now go to the other part, which is the penalized regression. Now, to do that, we require dereg. Dereg is actually, from dereg, you get function for discrete variable. Like I mentioned earlier, JLMnet for penalized and the rest of them. So let's say what command do you need to simulate the required data? Can you scroll down, please? Okay. Now, if you run line 66 down to 71, you can say no, say number of sample. That's what knobs mean there. And you want to run from uniform distribution. You want to run from uniform, want to simulate from uniform distribution. You can see that uniform distribution we have A and B, Abi. Lower, uniform distribution is continuous. We have continuous uniform and we have discrete actually. But in this case, we are looking at 0 to 1, right? 0 to 1. So if you run that, it's going to give you independent variable x1, and it's going to replicate that 1,000 times. It's going to give you 1,000 samples. Okay. Now, if you do x2 is between 0 and 2, x3 is between 0 and 1.5. Those are the independent variables. Then x4 is 0 to 3. Then x5 is 0 to 1.8. So now let Dr. K finish installing. I think when it's done installing, then we can continue from there.
Please, if you have any question, put it in the chat or raise up your hand. I can unmute you. If you have any question, raise up your hand. We are all learning in one way or the other. So please don't keep quiet. I think we are good to go. Okay. Hello.
Continue.
Okay. Is that error in data frame?
Where?
Everything no.
Okay. Please, scroll up, please. Let me see where the fault came from. No, from the result.
Okay.
Result, the lower part. Okay. Okay. Your X1, X2, have you?
Yeah, they are here. S1, S2.
Okay. Okay. Scroll down a little, please.
Up.
No. Down on the output part. The result part. I want to see that part that contains X1, X2, X3.
Okay.
No. I mean,
should we start from here?
okay, run again. Run from here again. Let's see. Knob 100. Did you do from 100 from 66?
Yes.
Okay, let's do it again.
It's 1,000. You put there.
Yes, knob equals to 1,000, line 66 to line 71.
Okay. Now we are 71.
Okay, you can now do add x1. Let's see the output. Add, so that the whole thing will not come out.
X1.
Just type it in the lower part. Add x1. The lower part. Okay. Add x1.
In brackets.
Yes, in brackets. Let's see if it's actually produced. It should. Otherwise, it will have given error. Okay, and let's run it.
Yeah, it's okay.
So, okay. 73 to 70, is it not 8 or so? Let's see those ones. Those are the parameters.
Okay.
Those are the parameters. Okay. Now, let's now pick 80 downward. That's is for the response variable. Like I said earlier, beta is equal to what?
So that's where the
2.8.
problem lies.
Okay. That's where the problem is. So what could have been the problem? Did you call dreg?
Yes, I did that.
Let's call it again, please. Required dreg or library dreg. Okay, just the dreg. Okay. All right. Okay. Now. All right. Okay.
So error in beta equals to 0.
Beta. What's beta? No. Let's remove that hash there from that beta. It has to be defined. There's no need for beta there. There's no need for that hash there. This, have you seen it?
Which of them?
Line 80. Line 80.
80, yes.
Yes, let's define beta. Beta is not defined that way. Remove that hash there.
Hash, okay.
And run it. Run it from there down. Yes.
Okay. I think it's better now.
No more error, right?
Yeah. Okay. We have our mean.
You can see that our mean is what?
2.195 and variance is 1.77.
Okay, this something is blocking my own here. Okay, I'm coming. So our mean is greater than what? Our variance, which shows that is an underdispersed data. So let's now let's proceed from there. Now let's declare our variable as matrix, our x. So let's have it, let's have line 92.
Yes.
Okay. If you want to see what it looks like, you can just say add x. And let's see what our data look like. Add x. Add. So let's run it.
Good.
So we can see the data in matrix form.
Okay. Yes.
Now let's now split train and test. I will be running, like I said earlier, set seed. It gives you the starting value, initial value here, so that when you have to do this again, you have the same result. So let's run 95 to 99.
Okay.
Wow.
So now you can see, like I said, this is a count. What we have done is to simulate count response. And we can see that our test is how many did we, it's okay, it's 500 actually. So you won't see anything like 2 point something there. It has to be count. Okay. And we can see that it has some zeros. So that means is zero inflated count. Okay. Anyway, let's proceed to line 102 and 103. Now I want to conduct our ridge regression for X training data and Y training data, alpha equal to 0, lambda is 100. That lambda actually means the tuning parameter. The larger the tuning parameter, a larger lambda usually we shrink the what's called coefficient to 0. Okay, so if it's large. But if lambda is 0, it reduces to what? To OLS. Okay. So let's see what it gives us. 102 and 103.
Yeah.
All right. So we
We
can
have
see
6 by
what
1, which
it
pass
looks like.
notice.
Okay. So let's go to our MSC. We want to find our test mean square error. Okay. So the formula is already there. Okay, you can see the formula. So we run line 1092 111. We'll see what it looks like. Okay, that has been done. So you can see. Okay. All right. Let's proceed to the cross validation. Line 114 and 116 up to 116. Okay. We can see, look at our mean square error. Does it resemble what we have? And I look at where the red line starts from. And we got 1 point what? The other time 1.8. Okay. Let me see. 1 point what? Okay. All right.
1.22.
Okay. So now we can see what it looks like here. You can see where the red starts from. This is just to further discuss the results. So what line are we, sir?
Line 122.
Oh, 122. Okay, fine. So let's conduct our cross validation.
Sorry,
Line
before
105.
122, you are trying. Sorry, sir. You are trying to explain the graph.
Yes. We see the y-axis here is actually represent the mean square error. And you can see at which call is this? Okay. Now we can see that at any given, when we look at this point now, when our log lambda, our lambda is 100. It's not, what do we use as lambda for that particular analysis?
Let me see.
Let's go back there. What do we use for lambda?
100.
Is it not 100?
Yeah. We use 100. Should we run it again? Are you there, sir? Dr. Olumide. Okay, people can hear. Let's just hold on.
Online on the phone.
Okay.
I'm back on the phone, actually.
Go ahead.
But that one of the system is one I see clearly. Okay.
You can log out from your phone, from your laptop. So that you just focus on the phone to talk. So at this point, what we are trying to do is we follow the same thing we did during the slide. That was what he's trying to explain to us. We've run the rigid and we are in k-fold cross validation to find the optimal lambda value.
I'm back.
Are you back, sir?
Yeah, I'm back.
Okay, go ahead.
Yeah, I think we used lambda to be 10 100, Abby?
Yes.
Okay, if lambda is 100 and we have log of 100 is 2, Abby?
Mm-hmm.
Oh.
Log of what?
Log of 100. When we find log of 100 to base 10.
Okay.
I think it's 2.
Okay.
Right. So we're working in base 10. It's going to be 2. So maybe to show our people so that they will know. Okay.
You right?
So now looking at this log lambda, we look at when we trace it up, it should give us something around that mean value, mean square error. Yes, it should be around that. So that's what is just telling us actually. Yeah, that's what it's just trying to tell us.
So what line?
So, now, here now the next line we did, we get our best lamp, because when we do our cross validation, it gives us a cross validation when we conduct it. It will give us lambda for all the what was it called? The data point to give us our lambda. But we have to choose the best lambda, the best cross validation lambda. That is what we are going to use to fit our model. So that is what the cross validation is all about. And that has been determined. So we can now move to line, what are we now?
123.
Okay, yes, we talk about the SSC, you know, the outs. Where are we? Okay. Then we want to predict now based on the best slam. Right. So that is what 126 is telling us. So the CV, the cross validation, the model now based on the cross validation now, alpha equal to 0 gives us, produces that. Which one is this? Okay, now we can see the lambda, the minimum lambda, we can see the least, well, this thing is not really, okay. All right. Then we have our index, we have a standard error, and the rest of them. So based on the outputs, okay. Now, we will look at 30, say, find the optimal lambda that minimizes test MSC. Don't forget that the reason why we do cross validation is to identify, to give us a minimum to reduce the mean square error. So based on that, we now look for the best, the minimal one. That's why we have to best lambda. So we have CV model, then best lambda. So that's what. Now we are not going to use that to now fit the model. Now you can see that's what we have in 135 and 136. So this now represent the coefficient now, the coefficient of our based on the model. So now next, line 141. Line 141. Okay. So it's just telling us, it's just identifying, okay, let's choose another set of data and conduct our prediction. That is what that one is all about. So use fitted best model to make predictions. And this is the output. Okay, let's proceed. Okay, so we now find the SST, the SSC, and the MSC based on the predictions we have done before. Okay, so all these ones. So have we used the LM Ridge? Have we gotten to LM Ridge?
No, I think so. I'm not sure. Let me check.
Let's go.
No, we are going there now.
Let's now go to the LM Ridge now. Let's go to the LM Ridge. It's a package. Inside the package contains function that it will produce results without having to write too much code. So let's now go to the use of LM Ridge package now. So if we have installed the LM Ridge, then we call it. We call the LM Ridge. So are we there?
Yeah.
Okay. So let's if you have brought the LM Ridge in, we now go to line 63, 163. Line 163. You will
So
see the result.
He's already analyzed this.
Okay. With this now, we have our R square, another R square, degree of freedom, our F, AIC, and BIC. And our coefficient, you can see the estimates Okay, you can see there are coefficients there. Okay, so our AIC is archaic information criteria and BIC is Bayesian information criteria. Those are used for model selection. Okay, now let's now go to the plots. The first plot. Okay, okay, which plot are we now?
Yeah, let me just start with first plot again. This is the first plot.
Okay, first plot. You can see that the coefficients, okay, the beta now, looking at the first plot, we can see on the left hand, right hand corner, you will see all the what red starts from, green starts from. I can't see it clearly. So those are the things that determine the coefficient. You can see the coefficient there. So the coefficient there is actually represented here. And you can see that it ranges between 0.1 and 0.67. You can see. So that's what this is. That's what this represents. All these coefficients. That's what it represents actually, with those dotted lines. You can see that we have 5 parameters there. You can see. So that's the first one. The second one, and we have the second. Okay.
Second graph is here.
Okay, just a replica of the first one. Then the third one. Okay.
The third one is there too.
It's there, okay. So like I said, this one still represent the coefficient, actually. Then I think, is it the last one now?
Yeah.
Okay. Okay. Now, this one, okay, the minimum MSC is 0.06. Our K is 0.05. Don't forget that your K is your best lamp. Don't forget, it's your best lamp. Okay. Now, is that all the plots?
No.
It remains one, Abi.
The last one.
Okay, let's have it. Thing is to give us generalized plot, a generalized CV and ordinary CV.
Okay.
Okay, so you can see now, you can see the minimum GCV, minimum CV. What this one is simply means is that you can see the upper one is generalized, the lower one is ordinary CV. Okay, so what it's telling us is that if this generalized CV is out of sample forecast, what happens to your cost variation if you are subject your data to out of sample? I think you know, out of in sample contains the prediction you make within the provided data set, but out of sample is the one that goes beyond the given sample. So this is telling us that even out of sample forecast prediction will give us a better CV because it's lower than that of what? The ordinary CV. So that is what is saying that, okay, this particular procedure is robust to out of sample forecast. So that is just what this last plot has given us. Okay. So
can I ask a question? At what point do we use cross validation plots? At what point?
Well, basically, all these plots we have here, they are just replica of the result already obtained. So what we use the plot to further buttress the results.
Okay.
Yes, but this particular plot, like the last one we are talking about here, is actually, we know our CV has already been obtained. We know our minimum CV already. Then we know the best line, which is equal to 0.05. So But this particular one is telling us that, okay, if you subject our data to out of sample, then what happens? So that is what this one is giving us. Then the CV is just the initial one that we have. So, all right, should we, okay, Lasso. Well, Lasso, let's run Lasso. We will be a bit fast with this Lasso because it's just a replica of what we have done. You can see, let's just stop here. Let's stop here, please. Let's stop here. Look at what happened in the case of Lasso. In the case of Lasso, you can see that the coefficient has been shrunken. That has been shrunken to 0. It's telling us that, well, the intercept is the most important variable there. And the intercept is a starting point for every analysis. Is a constant, like a constant. So that is what is telling us that, okay, what happened to dependent variable can be described by the intercept, the constant point. That's just it. So the remaining variables have been shrunken to 0 means they can be dealt away with. They can be ignored. So now this particular one has done variable selection. This Lasso has done variable selection invariably. So, and that is it. So whatever that thing we obtain as is a replica of the ridge that we did before. All those cross validation, all those MSC, you will see the code that they are similar, only that our alpha was changed to 1 in the case of Lasso. But in the case of Ridge, we retain alpha to be 0. And that is just the difference. So can we scroll down to the end? I think towards the end. Let's just scroll down towards the end. So we can just run everything and let's see what it looks like. Okay, look at them. Okay. So, okay. So we have all this. Okay. So you can see our R squared there is showing that it's a good model, 0.99 something. So unlike in the case of last Ridge, the model performance, was not really that, the R squared there was not strong. The closer to 1, the better. But this is telling us that our R squared, our model here is a good fit, a good model for the data set. So now, look at the exercise here. And I want you to carry out this exercise. You are going to conduct Ridge and Lasso for over dispersed count data. Now, what is this telling us? The one we did was for under dispersed. And look at the condition of beta. If you are defining your beta will be between 0 and 1. So between 0 and 1. That's for your far over dispersed. And you have to check if it's over dispersed, obviously the variance will be more than the mean. So when you do that, you now replicate this analysis. You get your results. Then let's see how your results, what happened thereafter, and how we're able to do that. Now for third exercise, can you please scroll down, please? For the third exercise, you go to ResearchGate using this link, download this data set. The data set is called hinsurance.cv. Now, what is telling us is that there's a data set called Insurance, health insurance. Actually, the response variable is number of encounter, which is accounts, the account data. Then can we show that variables? Okay. Sorry. It's not that clear. Okay, yes. Now we have predictors. We have sex, age of patients, number of encounter means number of diagnoses, number of period, number of diagnoses for the number of period visits. You know, if you visit a medical doctor for the period of number of times I've visited, you have number of diagnoses. Then the next one is individual on, yeah, let's see the next variable. Follow-up. Some people are on follow-up, particularly people that have hypertension. They are on follow-up. People that have cancer, they are on follow-up. So we use all these as what? As predictors. Encounter class. Are you inpatient or outpatient? So those are the things that makes up what the covariates. So, and that is what, that's a fit ridge and Lasso on data, right? Downloaded and discussed. So, like I said, the difference between these data sets and what we have done so far is for simulated data for this particular models. But now I want to use it on live data now. And the live data can be obtained from that website provided. So what I'm going to do, that is, you have 3 exercises that you're going to submit in the link provided, in the emails provided. We'll put in DataMind email, then you copy me on the other one. Yes. So that email is still valid for me. So I will receive it there as well. So at this point, we want to draw the curtain, but if there's any other thing that we need to still, is there any other thing, Dr. Okay, and or any other facilitator would like to add, or any participant, you're welcome to do that.
Any question? Thank you so much, our facilitator, for today. I want to use this medium to say thank you for the sacrifice. Putting this thing together is not that easy. We are all busy one way or the other. Even just to be relaxing alone is something, but coming out, teaching science is not that easy. So do we have any question? If you have any questions, a particular line is not clear to you, or you need more explanation, let us know. Or we should give you time to go over it, let us know. Ajayi Yetunde, any question?
Yes, sir.
Any question, sir? Ma?
I have a question.
Okay, go ahead.
Yes, sir. I need more explanation on the conditions for ridge regression, sir. When do we use the ridge regression?
Okay. Well, like I said, the idea behind penalized regression is to obtain results with minimal variance. And to do that, we introduce penalty. For ridge regression, we introduce lambda summation. Let's say J goes from 1 to N, then B beta subscript J squared. So that's for ridge now. For ridge. Are you getting it now? So,
yes, sir.
And to determine our lambda, we use the cross-validation approach to determine the lambda, what lambda would be. And you also know that the higher the lambda, the further the coefficient shrinks to 0. Are you getting it? So that is just the idea behind it. We want to obtain results, estimate with minimal variance. And you know that an estimator with smaller variance is more acceptable than the one with larger variance. You say it's more efficient. So we want to obtain an efficient estimate, right, with minimal variance. And that is why we inject bias and have a penalty. That's for Ridge. In the case of Lasso, it's absolute value of your beta subscript J that you introduce. The lambda is also there. The tuning parameter is there, notwithstanding. Right. So that is just it. And like I said earlier, when you use Lasso, Lasso shrinks your parameter, any parameter that is not relevant, Lasso shrinks it to what? To 0. But Ridge does not do variable selection. You only take your variable close to 0, but it doesn't do variable selection like Lasso do. Do you get it now?
Yes, sir. Thank you, sir.
Thank you so much. Faith Olaniregun, right? Do you have any question? Yes. Obon Samuel, any questions, sir?
No, sir, I'm good.
Oh, okay, that's fine.
Thank you, sir.
Odebode Sunday. Yes. Sunday.
Yes. Thank you so much, sir. I want to appreciate our facilitator tonight. Actually, when the machine learning lesson started last week, it kind of looks strange, but with the lesson and the teaching tonight, especially with the how to simulate data for fitting our models, which our facilitator have taken us through. So I think I'm okay with the lesson for tonight. I will just need to go over some things to be able to attend to the questions and also be able to practice on my own. So thank you so much, sir. I don't really have a question. Thank you, sir.
Yeah. Thank you so much. God bless you. Any other question? Okay. So can we just appreciate our facilitator tonight? Just put a chat there. Thank you, and God bless you.
You're welcome. So